at the end of the last session, we covered this continuing problem version of the policy gradient methods. Continuing in the sense that these methods are suitable for problems that don't have terminal states. So there's no sense of an episode. An episode will never terminate, and these types of problems typically have some sort of reward, goal reward, or some penalty state that you end up in. So like often you can reframe an episodic problem into a continuing problem. Like one of the examples we looked at in here was with the mountain cart, or with the cart pole problem, where in the continuing case, so normally this is treated as an episodic problem where you have a pole being balanced, and then if the pole falls below a certain point, then the episode is over. So then the goal is to prolong the episode as long as possible, which gives you like possibly some stability issues, because in theory you have this like infinite reward if you get a reward of like +1 for every step in the episode. But here you can reformulate it as a continuing problem, where here if there's a failure case, then you get a reward of -1. Otherwise you get a reward of 0, and if you get a reward of -1, then it resets the pole kind of like how an episode would restart. But here, instead of restarting the episode, we are just resetting the position of the pole, but still considering to be continuing on with the problem. So the rewards here are sort of inverted, where you get very rarely, hopefully rarely, this penalty reward. And then in this case, if you maximize the average reward, which is what we're trying to do in continuing problems, this would have an average of 0 if we never failed. So that would be the ideal situation. Whereas in the episodic case of cart pole, where we get this reward of +1, the ideal reward is infinite if we don't discount it, which technically is a problem. But then if we actually reach the infinite reward, we've succeeded anyway. So it doesn't matter. So I had looked at, I reformulated both the mountain cart and cart pole to be continuing problems. In the case of mountain cart, it's sort of the opposite of this, where instead of a failure, there is a reward for getting up the hill. Here, I can just show it. In here, there's this goal state. Here, normally this is an episodic problem where when you reach the goal, the episode's over. You can also do it as a continuing problem, where if you reach the goal, you get a reward of +1, let's say, and then you get reset into the bottom. And then you're trying, the average reward, you would reach the goal as frequently as possible, or in as fewest steps as possible. So that is, let me see, get back to this. Okay. Sorry. I guess that search term is not that great for getting back to chapter 13. So we had looked at, applying the actor-critic method to the cart pole problem. We'd already looked at it in the context of the value function methods, right? But now we're in the policy gradient setting. So, again, this problem, the original formulation of the problem, had a discrete action space, or so with 3 actions, kind of like the mountain cart problem, where you could either not apply any force, apply a full acceleration to the right, or full acceleration to the left. And that way there's only 3 actions. And here the policy function, we learn, is going to be something that assigns a probability to each of those 3 actions. So we can try to apply tile coding to this problem. And we can see here, so if this is the tile, so this is a parameter study of the tile coding solution. Now you can see here, like, when you do tile coding, in this case, the state space of the problem, there is the position of the cart, the angular position of the pole, and then the velocity for both. So there are 4 state variables that matter that we're going to use for the approximation. And then if you apply tile coding, where we break up each of those dimensions into some some size, some fraction of that dimensional size, and then we have also some total number of tiling. So here I've just kind of arbitrarily picked this a little bit to be something reasonable in size. This dimension here, this is the X position, and notice that this I have a coarser tiling than the others. The X position is like where the cart is on the track, so it has a limited space to move. If it goes too far either to the right or to the left, then it's also a failure. However, the actual position of the cart is not really important most of the time for the policy. It just can't venture too close to the edge, so it's kind of a waste to represent the X position like with a lot of detail, but you have some flexibility with tile coding. But you can see even with this fairly coarse breakdown, not too many tilings, we have like 29,000 features in this tile coding. And I'm going to do it in an efficient manner where these are binary features, they're very sparse, so I'm still using sparse representations for all this, and it does work somewhat. Like this is showing the training process. If the cart moves sort of randomly, this is about the reward average or the failure rate. If you divide this, so let's say it's like, if you take the inverse of this, you get roughly like how many steps it survives for. So if it's just sort of moving randomly, maybe it survives 20 steps, and then at the end of this training process, it has improved quite a bit to about this, right? 0.0, or no, not that good. So, like 100 steps. Here you can see like the actual time it survives. You can repeat this training and it does a little better, but this isn't doing that well as a solution. And I think part of the problem is that there's just a lot of features here and it's really hard to learn them efficiently. I am like trying to find with this like roughly where this works the best. I've already adjusted these lambdas to get something that looks reasonable, but we can look at what the policy function actually looks like. And here, this is the value function. You can see everything's kind of concentrated close to the middle here with the values, mostly 0 values out here. This means that when the cart starts in this initial position, that the preferred action is the 0 action, which is just to do nothing. If I move the cart, I can see like we can look at what the policy function looks like out here. So, and see in this position, which I guess maybe wasn't visited at all in the training process, it hasn't really learned anything. This is just a completely random distribution. We can go back, like reset this a bit to the middle, and we can see that what's down here are the probabilities for each of the 3 actions. So you can see like it's definitely learned something in this sort of band of space in the pole angle. Once the pole angle gets too far off, it has clearly not learned at all how to recover from that, which is why this purple color is just the random policy, because it's like a 1/3 probability. So this method didn't work that well for this. Now, it turns out even with a very small neural network, you can get a lot more success on this problem. Part of the benefit of using a neural network, like here the network's very small. There's just 2 layers of size 4. So it's like there's very few parameters. But the advantage is, I can take the 4 inputs and like that's the feature vector for the neural network learning. I can apply, a range squashing function to each of the dimensions. But, the input is just these 4 numbers, and then it can expand it out. Here it's actually not expanding it out. It's just keeping the same number of neurons in each layer. And here, if you look at the parameter study, like what did we get? What did it look like we got in terms of success? Negative 0.01. I guess in the parameter study, it doesn't look that much better. But if we look at, training it for an extended period, we can see we get a lot of improvement after, this is like after 10,000 steps. But as we keep going, and probably if I train this longer, it would do even better. But, this is the kind of performance you get when you do the neural network training. You can see like the cart, this blue line is the X position. So it is like sort of oscillating back and forth, well within the allowed range. The failure point here is 50. So, it's staying very far away from the edge. And, this is the pole angle on this axis, and it doesn't get anywhere close. So this is surviving, for a long time. What's being shown here, this is like 35 seconds. If I were to, show this for 10,000 steps, we can see this keeps surviving for a long time. I mean, eventually, this is because if it was trained longer, this problem would probably be eliminated too. You can see eventually it is starting to approach the edge more closely. This is already like an enormous amount of time compared to how long it was trained for. So whatever it's learned here can survive for a long time. But we can see like the policy function isn't actually that complicated for this problem. So here, like this is showing if the position of velocity is 0 in the x direction, then this is showing the policy function in terms of pole angle and pole velocity. Right? So you can see if the pole angle is to the right here, then the favored action, appears to be action 3. Right? And there's this dividing line here. So like really what the policy needs to learn are these partition lines in the space, which is very suitable to this neural network. I mean, these are practically, linear functions. It's just that we have this 4-dimensional input space. So while, for the tile coding, like it seems like this shouldn't be too hard to learn, just this clean dividing line here. The tile coding just looks like kind of a mess. Like it's learning some kind of partition in this space. But I'll show for the other problem, tile coding appears to be much more suitable and also only 2 input dimensions, which makes it a lot easier. So we can also see for this function, here I can just like choose a state, and we can see what happens like if I set the x position out to like 24, we can see what the policy function looks like, and we can see this surface is sort of shifted over where there is much more of the state space, which favors going to the right. And probably the reason for that is if it's over to the right, the policy knows that it has to sort of, go further to the right to get the pole moving to the left, so then it can correct its position back to the left side. We can also see here, this is showing the actual probabilities of the action. So if I like change the pole angle to the right, let's say, here we can see still, because the card is over to the right, it's still favoring this right action. But then if I move it over to the left here, then the policy is going to be balanced. Well, it's still favoring the right action. Yeah, this will now favor the left action. If the pole, angle is tilted to the left, obviously to correct that, I would have to move to the left to move it back to the center. And yeah, this little X here is showing, for this state where this action is taken, where we are in the state space. So here, see this, almost 100% probability of going to the left corresponds to, this action 1 in the high probability space, and here, low probability or almost 0 for action 3. And then the neutral action where you don't move at all is almost never taken. In fact, like the optimal solution for this might be like a very sharp line where you never really have any probability of this action. Here, this is showing the value function, which, so I believe if we reset this all to close to 0, we have a certain, so this is like trying to estimate the average value here. So, the average value is highest when we're sort of in the middle, which makes sense, because if the pole is in the middle, we have less of a chance of any kind of failure. As I move, if I set everything still pretty neutral but closer to the edge, these values should drop. let's see. Yeah, so now we can see like the average value is a lot lower. Um, and if the pole is even more in the right, if it's angled more to the right, it's even worse because we're already close to the right edge. And now we actually have to move to the right to fix the pole position, but then we're really at much more danger of going too far to the right. So, this all sort of tracks and makes sense. But, you know, clearly, like for learning this type of policy surface, you can see how you really don't need that complicated of a policy function or an approximation function. Well, like we certainly don't need, right, this like, like 30,000 features of tile coding, just which unfortunately is what becomes necessary when you have like a four-dimensional input space, because tile coding is much better at dealing with one or two-dimensional spaces. Going up just a little bit beyond that and it gets pretty unmanageable. But luckily this problem does very well with this technique. Now the mountain car problem. Well, first, are there any questions about the solution method or for cart pull?
No, I did not have any question, when you were discussing the tile coding and using the neural network.
Okay, so now the mountain car problem was in the book like one of the main examples used when we started the approximation techniques. So here again, I've made a continuing version of mountain car just to test these methods. So now here, if we reach the goal, which happens when you get far enough to the right, then you get a positive reward and you reinitialize the state. Otherwise, you get a reward of 0, right? So here we're trying to reach the goal as quickly as possible. And now, here is a parameter study of doing this, with tile coding again. So like tile coding was the method used in the book for this, and we can see with these are the learning parameters. So the values of lambda, and then this is for 100,000 steps. And we can see we could actually train this longer. It's learning quite successfully. And here, the value function has this spiral shape that we saw before. Now, the policy function, here I'm showing like the samples of the policy. But, this sort of reward, like this is as successful as any method we had seen earlier. Like this is getting pretty close to the optimal where, we're finishing in like, anything under 100 steps is great. We're just going, backward once and then forward again. And this is showing the actions taken throughout the episode. Now, this is only a two-dimensional state space. There's the position and velocity of the cart. And we can see that, like, tile coding is very good at making these arbitrary designs in, a state space if the actual number of features is reasonable. Like here, with this amount of partition, with this tile coding, I think it doesn't show it up here. I'll show it below, but there's only like there's less than 2,000 of these features in this problem. So, this 100,000 steps, there's plenty of samples collected to learn this entire thing. And in contrast, if you try to apply like a neural network to this problem, which you can try to do it with different sizes. Like here, the network I'm using is much larger than what I used for cart pull. And I tried this in different contexts, and you don't really end up with much. Like I'm not even showing that this doesn't even really work. Like it has, if you compare this is the average reward through the training process. If we look here, we're getting up to like 0.005, 0.006, and here it's like significantly less reward than that. So this is sort of randomly reaching the goal a few times, but it's clearly not learning very effectively. The policy looks, pretty random. And the value function, there's some sort of shape it's forming, but, for for a neural network to form this kind of shape in the state space is actually pretty challenging. Like for tile coding, it very easily has, these thousands of features. Like the nice thing about tile coding is there doesn't need to be any effect. Like all the effects are very localized. So you could learn like these sorts of features have a certain value, or this like part of the state space could have a certain value, and then it could very rapidly change to a different value. And in this spiral pattern, we can see that the values, like there is this pattern if you follow along it where the values are moving smoothly. But if you move through the state space in any kind of normal fashion, like going up or down, you get these really sudden changes of value, which is really hard for the neural network to represent. Like it needs a lot of neurons. It has to be very large. I don't know how large it would, and the larger it gets, the slower it is to train it. So it needs a lot more training examples to actually learn this. So here, it's learning just some smooth representation. And, I think for using a neural network is really effective on problems where the natural input dimension of the state space is really high. Because then what you have to do is deal with this high dimensional input space and find partitions in it that, like, the neural network is really good at dealing with high dimensional input spaces. What it's really bad at is taking a very simple input space, like here is just 2 dimensions, and expanding it to possibly thousands of things, which in order to recover something like this. But this is much more efficient because here all these features are very sparse. Like what matters here like doesn't really affect these other features. And the neural network functions are much better at building these like smooth functions where a lot of the parts of the state space affect one another. So it's very bad at like isolating parts and just making a very sudden change to like this corner of the space without affecting anything else. So I don't know. I didn't test this long enough to see like how large of a network I would need to actually have a good solution to mountain car, but it's not really worth trying for this. It seems like if you have this, low dimensional input space, at least for like testing purposes, this method is really good. Plus, it's a linear method, which makes a lot of convergence properties better if you're sort of searching around the space of parameters and not sure what you're doing. So, okay, so those are the 2 examples. I am going to revisit them for the discussion of this continuous actions. Now, so far, like these are following the same pattern of discrete actions that we've used in the book so far. So with discrete actions, like in the case of cart pull and mountain car, there are these 3 actions, like -1, 0, or 1. It can be rescaled up to some like appropriate force value. But we don't have the ability to accelerate like with less than full power. Like there is some set value that we can choose. And the idea behind continuous actions is to, we still want a stochastic policy, but we want it to be able to take on any value. So here, the example used in the book is to use a Gaussian. And, a Gaussian has 2 parameters, the mean and the variance, the standard deviation. And we can build a function where the output of the function, instead of a probability distribution, like here I'll show. So here in the discrete case, the policy function produces a probability for every action here, the 3 actions. Here we're going to produce, our probability function is going to output 2 values, one for mu and one for sigma. And then when we choose an action with this policy, we're going to assume that this mu and sigma are the parameters of a normal distribution, and then use that distribution, sample from that to get the action. And that way, the policy can tell us the probabilities that we should use across this entire input space. So, here, like, this is a normal where we can freely move this. This is moving the mean around. And then, the sigma just controls how sharply peaked it is. So as sigma approaches 0, right, this gets more and more sharp until it becomes just a delta function where it sort of stops being stochastic. And then as sigma goes up eventually, we just get this, we have an equal probability of anything on the number line. Now, of course, sigma has to be a positive value. So one of the caveats here is that if we use linear approximation, like here we're using an inner product to compute mu and sigma, when we compute sigma, we're just going to allow this inner product to be, right, any value. And then if we take the exponential function of it, that guarantees it to be a positive value. So that way these parameters can be anything and it won't screw up the distribution. I mean, there is still some numerical stability issues with this. You can get sort of infinite values, undefined values, right? Because, if the policy function tries to generate values that are like very high means or something, because this is totally like unrestricted. Mu could be anything. There's nothing stopping it from pushing the values higher and higher, and then you end up getting, infinities and dividing by infinity, possibly then producing nan values. So you have to be careful about the learning rate here, because you can end up getting like not a number values in your parameter space. And then there was this, I showed it a little before. If you're interested in all the math, you can look at the exercise solutions here. But this is how you derive the eligibility vector for this, where, right, we have to take the natural log, the gradient of the natural log of the policy function. So here we have two sets of parameters, one for mu, one for sigma. And this is for linear approximation, this is the functional form of the eligibility vector. And, of course, when we compute it for sigma, we have to make sure we're accounting for this exponential function. So here, if you look at my solution to exercise 13.4, you can see the derivation of the eligibility vectors. It's not too long. Well, sorry. It's mostly like, chain rule stuff and, knowing how to, like quotient rule, product rule, chain rule. It's pretty standard. There's nothing really too crazy you have to do with this. Oh yeah, there was also, this exercise is kind of interesting. This is evaluating the eligibility vector for a logistic unit. Now, this is good if you have a problem where there's only two actions. So we actually haven't seen that. The examples I've shown before have 3 actions. And, when you have 3 actions here, we want our function to output a probability for each action. Now, if you only have 2 actions, really, you don't need to output a probability for each action, because the second action is just like the probability of it is 1 minus the first action. So we can actually get away with just outputting a single value, and that's a little more efficient. And that's what this exercise 13.5, if you instead just output this single value of this logistic unit, then this is what the eligibility vector looks like for that. So this avoids the need to use, like the policy gradient stuff we had before. This is not really for continuous actions, though. I guess it's just kind of related to it because of the neural network activation thing. If you were to, you could also approximate these with a neural network instead of these inner products. Like, this X could be the output of some neural network, and then you would just have to apply the chain rule going backwards. But usually, the output of the network itself would be this linear layer. So you can still use this result to do this with a neural network. But, this is just showing it for pure linear approximation. So, one of the problems with this is, in the problems we looked at so far, there is some, logical limit to what the action can be. Like in the case of mountain car, the action of like +1 has some force value in mind. And it's also a value which is deliberately chosen to be too low to actually just power your way up the hill, right? So like here in the mountain car problem, if you start in this position, you have to go backwards first in order to go forwards to build up enough momentum. Now, if you instead treat this as a continuous action problem, you have to have the actual, step function of the problem deal with these if the policy tries to output a higher value than is reasonable. Like here, if the max value it should output is 1 and it outputs a value of 4, like how do you handle that? Well, either you can just, clip it, so, it doesn't care, it just acts as if you applied a value of 1. That's one way of dealing with it. You could also penalize it, where if it outputs a value that's too high, it just acts as if it's outputting a value of 0, or a very low value, maybe like as if the wheels are slipping. That's one way of doing it. Now, if you don't do anything to it, you're just going to have a force being applied which is larger than intended. So that's if you're using a normal distribution for this. There are distributions you could use that would naturally restrict the values in some range. So like here, like this is a beta distribution. If both alpha, it also has 2 parameters. This is the functional form of the beta distribution. It is a little hard to deal with computationally. There are these, these functions which, like, if you use a special functions package or something, people have already implemented these. But like, the beta function, the gamma function, the integral of the gamma function, like these are all things that are pretty expensive to calculate. But you do get this distribution where the distribution is only defined from 0 to 1. Right, so as we change the value of beta, like if beta is greater than alpha in this way, then, we favor like the 0 action. And then as we move, if they're sort of more equal in value, you get something that looks more like a bell curve that lives like in the middle of this. And by adjusting these two, you can move this distribution back and forth, change the variance. So this is one option to use. Another option, which might be a little more practical computationally, is this squashed Gaussian. What we can do is start with a Gaussian, and then we can say we want to consider a new random variable y, where y follows a distribution that looks like as if we had taken the tanh function on x. So the tanh function, also used a lot in neural networks, is just something that squashes x to between -1 and 1. So there's just an asymptotic limit on both ends. As x goes more and more negative, you just limit at -1. Positive on that end, you limit at 1. And you can use this change of variables theorem in probability theory, which just says that if we know the way the density function for the original random variable, and we know this transformation function we're applying, we can get the density function for the new random variable. So here in this case, the g function, the thing that the transformation function is tanh, and the tanh function is just this this shorthand for these exponentials. And then we need to apply the inverse tanh function. Luckily, this tanh function is easily invertible. And then we also have to calculate the derivative of that inverse, which happens to be just 1 over 1 minus x squared. So this is what the density function looks like for the squashed Gaussian. So it looks almost like the Gaussian. We have this inverse tanh replacing the x in here. And then this is just to normalize it so that when you integrate it over the line, you still get an area of 1. This normalization factor will end up not mattering in how we're going to use it. So really, the only difference is that instead of sticking our variable into here as x, we just apply the inverse tanh function to it before putting it in there. And now we can plot this density function it ends up looking a little different from the beta distribution. So here I'll show, let's set the mean to be 0. So in a normal Gaussian, this would just be a standard normal bell curve. Here, because here I've set the maximum value to 2 actually. So if I reduce it to 1, all right, so now this distribution, like this is what we wanted, where there is 0 probability of the value being, outside of 1 or -1. So what's happening here is all the probability that would be, spilling out into this part of the curve is now getting squashed at the ends. So we end up with this bimodal looking thing. If we increase the variance even more, it becomes more extreme, which now this looks a lot like the beta distribution we had. And then if we make this much smaller, we end up, getting something that looks more like the original Gaussian. It still is abruptly cut off here. We can move the mean, and we can see as we move the mean like closer to the left side, now this is getting, again, squashed into the left, right, instead of, spilling out because of that, this, hard limit at -1. You can see the same thing on the right side. So this is just an alternative to the beta distribution of restricting the values in a certain range. And we can also extend this a little bit by, changing the maximum value, right? So we can make it a little bigger. That would just mean this g function becomes, whatever that max is times tanh of x. But all the math is, it's not any harder by adjusting this maximum value. And if we set this max value to infinity, then this just will limit to a normal Gaussian, where the max value won't affect it. I could also, restrict this down a lot. Or now, right, if you want something that sort of roughly like covers the whole space of actions, it's just a matter of choosing the right variance value. So now, this now does not look like a Gaussian anymore because the top is all flattened out. So that's the effect of this transformation. But, it might be helpful for problems where you want the policy function itself to take into account this restricted range, as opposed to having the step function deal with it of, whatever the environment is, like however you're simulating the environment. Are there any questions about these probability functions? The eligibility vector for this squash Gaussian ends up being pretty trivial because this action variable in here, right, this is not a function of the parameters. It's not going to be affected by these gradient calculations. So all we have to do is just, wherever we had a, we just replace it with the inverse tanh of a. And the normalization function doesn't even matter, because when we calculate the eligibility vector, right, we're dividing, we have the gradient of the policy, and then we're dividing by the policy. So any constant value, like this is a constant with respect to the parameters, it just cancels out when we do this division. So we don't have to make too many changes to this. And like practically, you usually do have a maximum value in mind for the actions. So this is probably most of the time better than just using an unrestricted Gaussian. So what follows here is a bunch of code to implement these continuous actions. I do have to make a new like MDP type here, because the normal MDP type has a list of the actions for the discrete actions. And here that is replaced where we just know like the type of the action. Most of these algorithms are only going to be defined for actions that are like either a single value or a tuple of values. We're only going to consider actions that are a single numerical value. Like in the case of cart pull and mountain car, it's just the force being applied to the vehicle, and that's just a single value. But you could easily extend this to having multiple forces as long as like they're not related to each other. You can just have a separate distribution defined for every dimension of the action space. So you have like four different forces you have to apply. You just have parameters that learn the mean and variance for all four of those actions instead of just the one action. So we have, and I have this a version of this for the Gaussian, for the beta, for the squashed Gaussian, and then also it ends up re-implementing reinforce and the Actor-Critic method. So now there's a lot of different methods available, right? Because like if we choose to handle the problem with continuous actions, but we also have the reinforce, the Actor-Critic method for the continuous actions, and then we could also treat it as either an episodic or a continuing problem, which is also a separate set of algorithms. So you can do parameter studies for all of those methods and see what ends up being working best. Another thing I was going to do here is update the parameter study code so it's easier to just randomly sample a bunch of things and save the results. Right now, the parameter studies that happen here, I could show them. They're like these curves I showed earlier, but they're just sweeping through like one learning rate and keeping some of the other stuff constant. And once you start adding all these different parameters, it's easier to just kind of do like a random scatter shot across a bunch of these things and just rank the results. And you can keep accumulating new results and seeing if there's any kind of pattern. But okay, wait, this is from what I wanted to show was for mountain car. So now this is we already saw the mountain car solution, right, for the discrete action space. And now, yeah, this is the same kind of thing. Actually, what I'm showing here, what I showed earlier with the mountain car policy, what it learned, right, was this, where this is showing the sampled action where red is accelerate to the right, blue is to the left, and then gray is nothing. Because now this is like a policy, right? These are all stochastic policies. So we can actually look at the probabilities themselves, and this is just showing the actual probability heat map for the three actions. So you can see like in what part of the space each action is favored, instead of just the random samples of them. Right, but the value function looks about the same. This is for the episodic case of the problem, though, instead of continuing. So here the values are much larger because here the value corresponds to the number of steps that are expected before reaching the goal. So similar solution. We get some like 100 and something steps. Now, this is showing if you take the mountain car problem and you want to define it for continuous actions. Here I've defined this sort of slip force value. So the intended maximum force you're supposed to be able to apply has a value of 1. So here this says if you try to apply a force greater than 1, then it takes the sign of that force and just makes it a tenth of that. So it's as if like you're just spinning the wheels, applying a much smaller force. This could also be set to 0 or just be capped out at 1. Either way, there is no point in actually applying a force greater than 1. Because here I'm going to apply this continuous action method with Gaussian actions. So here is an example of training with this. I did the parameter study is a little hard. You can see like these are messages given during the parameter study, and you can see that like invalid continuous action of not a number taken in this state. And this is because of the learning rates involved, the parameters have gotten to a point where at some point there was an infinite value. It turned into a not a number value in the parameters after that. And now the policy function is ruined for this training process because like you can't do anything with these not a number values. You just have to reset it to an earlier point and recover the training from an earlier process. So this means that when this was training and in some area I was testing, whatever the learning rates were, it was producing, you know, sort of garbage results. So here is an example of learning parameters that succeed at this. And now we can see this is the action selection. And now this is being sampled with this Gaussian policy. You can see sometimes it actually is selecting an action which is greater than 1, right? In this case, it wouldn't be a good idea, but for the most part, in the part of the policy that matters the most, like this, these first 3 sort of acceleration phases, it's actually staying within 1, or at least, you know, it's learned that there's no point in producing a value outside of 1. So this was able to learn, you know, to not become unstable and go into these regimes. Now, if I make, as just an example, I'll make this learning rate larger. So now this will now probably produce a policy value. If not, I'll make it even higher if this still works. Okay, I don't know why this is taking. Okay, so that was learning rate that was higher, but it didn't actually produce the kind of failure I was talking about here. I'll make it even higher and see. Okay, yeah, so now we have this not a number value. So now we can see that it was learning the policy function, and now there's this part of the policy space where if you use, if you calculate, you know, the values or the policy probabilities, right, you end up with like not a number of values. And now we can't use this policy function anymore because we don't know what to do in this part of the state space. So this is, you know, the learning rate is too high in this case. So I'll set it
So
back
is
down.
there an explanation of why, you know, the learning rate, you know, causes a divergence of the policy completely?
Yes, so it mostly has to do with, you know, if the variance, like if sigma gets to 0, I mean, or close to 0, that's a problem. You start getting infinite values in here. So if the policy is, you know, I mean, there's no guarantee that it's going to correct itself during training. Like it could be trying actions that are have a very low variance. So you can kind of look at these two equations for the eligibility vector, and you can see where there are problem areas. I mean, so definitely one problem area is if sigma gets too small. I mean, here we're also squaring it in both places, so it doesn't even have to be, you know, like 1 over sigma could be reasonable, and then 1 over sigma squared could be infinite, right? And we're taking the exponential function here, right? So that ends up driving this inner product to just a very, very large negative number if we want to produce low values of sigma. We can see here actually what, okay, so this was successful. If I said what? If I set it to -3 here, this is where it failed. So we can see, so policy parameter 2, this is what, this is sigma. This heat map represents sigma. This heat map represents mu. So what we have, it appears, is that this part of the policy, right around where before it fails, is that the value of mu is like negative 23,000, right? Of course, the value of -1 is the point where, like, beyond which you don't get any benefit. And then sigma, this is like a value of 12. So then, you know, we're taking the exponential of that. So e to the 12 is like this very large number, right? And then if we take 1 over this squared, it's probably pretty close to 0. And actually, if we use like float 32 instead of 64, wait a second. Yeah, okay. So it's still not quite 0, but you can see if this gets a little bit bigger, which apparently it's on its way to, like if this ends up being like 17 or something, yeah, this is gonna eventually hit a 0 value.
Aren't there numerical tricks in order to make it more stable?
Possibly. I don't. Well, I mean, the trick is, I mean, you know that like the parameters can. Oh wait, sorry. This is
other than changing the parameters.
Changing the parameters. Well, if the learning rate is too high in any stochastic like gradient descent scheme, the parameters can diverge. Like that's not a matter of applying any numerical trick. It's just if your learning rate is too high, it's a problem. Like no matter what. Now, yeah, you can do. You can make sure that any gradient step that you take is just like restricted to a certain size, right? So you can take like the vector. I mean, it's a little hard in here, but if you compute this gradient, right, we're going to get a different value for every parameter. And you can take that entire like delta vector and you can restrict it to a certain magnitude. And that way, like regardless of what the learning rate is, you can still keep the step within a certain size. So that is one trick that you can use. Just like you could do that with any gradient descent scheme to prevent the values from diverging. And yeah, I'm sure there are other tricks that you can use. I think like this distribution probably has fewer problems than some others that you can use. But yeah, I mean, one of the main issues, yeah, it would be actually this. Yeah, I know. Yeah, sigma being too small would cause a problem. But you could see like one of the problems in the solution I just showed was clearly the values of mu going really to extreme values. And I think the issue there is just like here, like you can see even with this learning rate, it's still peaking at some of these values of like +3. If this was trained longer with a small enough learning rate, it would learn, to keep it more within this -1 to 1 range. But, this is completely unrestricted. So when you do this with normal policy gradient with discrete actions, you can push the probabilities to extreme values, but, the most extreme probability is like 1 or 0. In this case, you can get, I showed like the values of mu were getting into like tens of thousands. And, at that point, just like, the values are just getting too large to deal with. Here, like you get a value of like 10,000 and then you're squaring that. So it's probably a problem there. But yeah, I think if you have this unrestrained Gaussian and the learning rate's too high, you're just going to very frequently get, these values, the actual numerical output, like of the samples are just going to blow up. But I will show, like, this is one reason to use the squashed Gaussian, because you prevent that problem. And hopefully the way the training works is, I mean, you can still get problems with like the inverse tanh function, as you get to the extreme values. Like other things can go wrong if the learning rate is too high, but at least you don't have the problem of the samples, themselves reaching these enormous values. I will one sort of, this might be kind of obvious, but I made this other version of the MDP. Here, it's actually defined up here. So here I'm saying, like, now I'm going to make this slip force 100, right? So now this is 100 times greater than is intended for the problem. So now it can apply a force of 100, and it will actually apply a force of 100. The velocity is still capped at 0.07, but the force is now, much higher than intended. And of course, now it makes the problem trivial. This, I didn't even adjust these learning rates or anything too much. But this is the solution it finds when you do that. Again, we have continuous actions. So this is like if I had forgotten to correct for the fact that these actions can get very large. So now, it starts here, right? It applies a force of, 80. So the velocity just jumps up to the max, 0.07, and then it just stays at the max velocity until the end. So the car just drives straight up the hill to the goal. It actually doesn't need to keep applying a force this high, right? That's why it tapers off. You can see all these force values are, much larger than 1. So here is, like the policy it learned for this. But you can see these values, like it doesn't even explore the rest of this policy space because it never had to learn to move around at all. Like all it does is, floor the acceleration, go as fast as it can straight up the hill. So, doing this actually makes the problem trivial, as you would expect. The whole point of the problem is the force is capped at 1 or -1 so that you can't do this kind of thing where you drive straight up the hill. But, it is kind of amusing that when you remove that cap, you can see, like, it's a good way to test this algorithm where it is successfully learning how to, cheat in the problem by applying a larger than intended force. But now this is the same problem now with the squashed Gaussian. And here we can see what the solution looks like. So now, the sampled actions, they are, mathematically restricted now between -1 and 1. That's just the default range. With a different problem, you could choose a different range, like -10 to 10 or something. This mountain car problem already naturally had, like, the applied force is -1 or 1. And, there's some intermediate values learned here, but these are the policy parameters it learned, right? So this is like, again, with the squash Gaussian, we still have mu and sigma, but the actual function, if I plotted that down here, this is showing for a given state, so position and velocity, what the actual distribution looks like. Right, so you can see for the values of sigma, right, here you have to take you have to exponentiate this to get what the actual value of sigma is. But we can see as we move the x position around, or like if the car is, far over to the left, obviously it favors taking this right acceleration action. And if we're still moving to the right, right, so you can see as opposed to the other policy, right, it would just be a Gaussian. So even if the mean was around here, a lot of the probability would spill over well past 1. So even if the car does learn, like, the only way it could deal with that is it has to make the variance much lower for these, whereas for the squashed Gaussian, it doesn't have to actually make the variance extremely low to really to cap this output value, because it's already going to be naturally capped at the edge. And we can see, like, if we start here, let's see, if we start like in the middle, so this is when the card is just right at the bottom, and we can see at the bottom it slightly favors going to the left, but I mean basically it has to move either to the right or to the left to get out of this. So this bimodal shape is sort of an artifact of what this distribution does when you cap it. It's unclear, like, the optimal solution probably is not something bimodal like this, but this at least is somewhat numerically stable, and it's an easy way of dealing with these cases of the actions close to the edge. But you can see like we still get the not a number values if the learning rates are too large. I can try the same thing here. I'll make this a higher learning rate and see what happens. Yeah. So here, like you can see, like the policy is somewhat working here. It's only this little part of the state space where it failed with reaching not a number values. Here, the not a number values wouldn't be from. Well, no, it actually could. Yeah, like the mean here is still free to become very large. Here, like these values don't appear to be getting too large, so it's a little harder to tell what's going wrong here. But it's probably something to do with the inverse, right? The inverse tanh function that I showed, right? Like as the values get, close to 1, like there are asymptotes in that function as well. So all these continuous methods, you do have to be careful of the numerical stability. Right here is another case, like learning rate's too high. Again, like the policy mostly working, it's learned something successful, but now there's this little square in the state space where the actions have become undefined. But yeah, this probably would be a good candidate for adding to the training algorithm something that caps the actual magnitude of the gradient vector that we apply. It's sort of like in neural network training, if you do like like max, you could do like max norm regularization too, where like after you take the update, you like restrict the norm of the parameter vector to within a certain size. And typically you would only use that with not nonlinear methods, right? This, I'm still using tile coding, which is a linear method. So you normally wouldn't do that kind of regularization with a linear method, but it's certainly possible. Yeah, like restricting the size of these gradient steps is more like, yeah, you can do that. So then if you encountered an infinite value here anywhere, you would just, cap it at whatever the max value is. Or if you're doing a max norm thing, you could make it so all the other terms of the gradient were 0, and for the infinite value, you just replace it with a value like 1 or something, or like whatever the maximum value is for the norm of the change. Yeah. Yeah, there were some other, you could also apply all these policy gradient methods to other problems. That is sort of, that's the end of what I wanted to say about continuous actions. Yeah, just wanted to show this squashed Gaussian. You could also try to solve this with the beta distribution, but the squashed Gaussian I think is probably, it's numerically better for most cases, and it's a very simple extension to the Gaussian. So yeah, there's this summary of chapter 13, which just talks about how the policy gradient methods differ from the action value methods, and that they learn these stochastic policies instead of all of the action value methods produced these deterministic policies where but policy gradient methods are very useful when we have these cases of function approximation, because there are like this corridor problem, which was one of the examples in the chapter, is a problem where you actually do need a stochastic policy to solve the problem if you're relying on function approximation. For the tabular methods in the book, for part 1, those methods, you always know the exact state that you're in. There is no uncertainty about the state, and for those, you can always use a deterministic policy for those. But here, for function approximation, which is all these examples we've looked at today use function approximation. Um, the policy gradient methods are more flexible, and if you do need a stochastic policy, they will work for that. And as a plus, we can also adapt them to these continuous actions. So that covers all of the methods in the book. Now we have a variety of methods we can study. We could do some other case studies of different problems. I guess now I can ask if there's any questions about the end of chapter 13, and then maybe see out of the people here what people would be most interested in looking at. Either like revisiting some of the earlier examples in the book using a mixture of methods, or looking at completely different set of case studies, or moving on to part 3 of the book. I guess I can also show the table of contents of the book, so you can sort of see a summary of what's in part 3.
So you mentioned that there were only 4 chapters at the beginning you don't have videos for?
Yeah, that's right. The first 4 chapters. I think the first video we have is on chapter 5, covers Monte Carlo methods. So it's the first like non-exact solution method in the book.
So if you were to have videos for the first 4, then you basically have a complete class, which might be really good. I have enjoyed the way that you have presented this, because you've gone far deeper into these than any other presentation I've seen. And I'll also mention, as an aside, uh, Google Colab now offers Julia in their notebooks as well, which means that your work that's now running in Pluto
Pluto.
could be ported over there as well, which would give you GPUs, which might be nice.
Yeah. Those are all Colab is all Jupyter notebooks, right?
Yeah.
Yeah.
But they didn't offer Julia until just this month.
Yeah, definitely. Like you could take um like all this code in the notebooks, the way I've set it up is um they are also like part of a package that could be imported. So even like the code in these notebooks could be imported into a Jupyter notebook in Colab and then used, and you could run individual examples with that. So yeah, that's certainly an option, and then other people could test or like share their results.
But your presentation has been far more detailed and nuanced than anything else I've seen on this topic.
Well, thank you. And I guess so you think it would be good to like redo the first 4, and with like like kind of like how, I don't know if I would change anything from what I did the first time I went through it, but
I wouldn't ask you to change anything, but having a recording of them, I think, would be very valuable.
yeah. So the last time we did chapter 1, it was like an introduction where it was also like kind of a kickoff for the whole thing that was like part of it. I think it would be a little weird to do sort of like a kickoff meeting, which then we do part of the book and then stop. So I don't know how that would go.
So I've rewatched the first 4 chapters again. If you were interested in getting a good recording of them, again, your presentation style is really valuable.
Okay. Well, we can. I guess yeah. So would you prefer to do that prior to doing any other like case study things, or like doing some more technique overview that looks at some of the examples, or
It's kind of up to you. The technique overview would be good. Um, the final part of the book would be good, but I don't think they would be more important than having good recordings of the first 4 chapters, which would create kind of a full thing, which would be done.
okay, yeah. So the next meeting, yeah, we can do that. the next meeting, like, yeah, the first four, I think, yeah, if I feel like doing some other case studies, I guess it wouldn't make too much of a difference just delaying that one session and doing some things. Because I was also adding some other like individual notebooks, more like kind of like a model zoo thing where there were some, like the mountain car example where you could import it and use it. So I was going to add a few more environment things like that. Oh, also it would be helpful to know if there was any particular like toy problem case study thing that anyone was interested in looking at and like testing different techniques on. I know there's like all the model zoo stuff from like DeepMind. So we could adapt some of those, but you know, if there was some other like custom problem that's not too bad to formulate like this, we could, you know, we could use it as a topic for one of the meetings. And here, this is just for people who want to know, this is part 3 of the book. This table of contents here, so you can see like chapter 14 is on like connections to psychology research, reinforcement learning theory. 15, I guess, is more on like, yeah, neuroscience and how like actor-critic methods connect to certain theories about how neurons work. And then I guess this is probably the most relevant one connected to the first parts of the book, is applications and case studies, which covers a lot of even like reads like AlphaGo. So this might be worth doing at some point, and even trying to implement like some of these like the backgammon program, checkers, and yeah, it would be. I know like a lot of people have done their sort of own version of AlphaGo, or like, you know, AlphaGo and like a Jupyter notebook, but that would be, I guess, probably an interesting topic too, to go through more detailed and like see how to implement something like AlphaGo 0 with all the little, you know, nuances that come up when you actually try to program it.
I'd be very interested in seeing the rest of the book, but not until after the wrap up of the first part.
Mm-hmm. Yeah. Okay. So then, yeah. So for the next meeting, we'll either like do one sort of method case study thing, or I mean, it could even be combined with like partially with the introduction, because the introductory chapter actually kind of, it mentions a bunch of examples and things that are even like a lot of them are pretty advanced topics. It's just an example of like what reinforcement learning can be used for. So I guess I could even show some of the case studies and solution methods as part of the introduction, to have, right, a sort of an example of like, here's like where we're going with this. You can end up having these solution methods that solve these problems. So yeah, I think it would work fine to do like a new introduction with some like wrap up overview of how the different methods work. So yeah, I guess we'll plan on that for next time. And then yeah, if anyone wants to like send me a message on Meetup or on Discord of a specific, you know, case study example that would be fun to try, let me know.